All right, so this is section, oops, what's going on here? This is section 3.5, and this is the double angle and half angle formulas. Or identities. So more identities, and of course that naturally means more verify type problems, and those verify problems now might involve these two new identities that we're going to talk about. So ultimately we're going to end up with verify problems that potentially can have a huge range of identities that you might need to apply. So I think they're nice exercises because they make you think about all the different possibilities. Should I use this identity, that identity? You know, you have to think about all the different identities in your arsenal. Okay, we're going to talk about the double angle identity first, double angle identities first. Formulas, I guess I'm calling them formulas here, but same thing. These ones are the kind of more simple ones. And then the half angle ones are a little more fancy. We'll talk about that right after we do this. So double angle formulas, the idea here is if I know cosine of, and our book now at this point likes to switch, has switched to using x and y's, or x's, sorry, in the identities instead of alpha and betas. So I'm gonna kind of follow that just to keep consistency with the book. So the idea here is if we know cosine of x, what's cosine of 2x, right? What's double cosine of double the angle, right? If we know sine of x, what's sine of 2x, right? And so on. Okay, so we want a formula for cosine 2x in essence, right? And in a way, we already talked about this when we talked about the cosine identities, because cosine of 2x is cosine of 2x is just x plus x, right? And the reason we're writing it like this is because now it's in the form cosine of something plus a second thing. And so we can use our cosine identity to say this is cosine of the first guy times cosine of the second guy minus sine of the first guy times sine of the second guy. All right. Now, of course, this guy can be nicely simplified. Cosine times cosine is cos squared x. Sine times sine, sine squared x. All right. And that's it. That's our double angle identity for cosines, right? So if you want to know cosine of double of an angle, and you know the sines and cosines of that angle, then you're all set. A quick application is maybe cosine of 2 pi over 3, right? So this is cosine of 2 times pi over 3. Let me put it like that, right? And so now we can just quote the identity. This is cosine squared of pi over 3 minus sine squared of pi over 3, which is, well, cosine of pi over 3 is 1/2, and so 1/2 squared. Sine of pi over 3 is root 3 over 2, and so that's squared. And so we end up with 1/4 minus 3/4, which is going to be minus 2/4, which is minus 1/2. Okay. All right. In degrees, this would have been cosine of 120 degrees, written as cosine of 2 times 60 degrees. And then we used the fact that we knew cosines and sines of 60 degrees. All right. Notice that this is actually not anything really new, because essentially we could have just written it as cosine of pi over 3 plus pi over 3 and quoted the cosine identity that we had before. But at this point, we have so many identities that there's a lot of ways. For a lot of angles, there's multiple different ways of calculating the same cosine or sine. Okay, so we do have some natural applications of this. However, this identity in particular is going to be super useful for us in just a few minutes, because the half angle identities are going to come directly from this guy here. All right, so this guy is actually particularly useful for our class. In the future, if you're going to be taking calculus, this will also be a very useful identity because it'll help you understand how to work with essentially squares of sines and cosines in a nice simple way. Because in the future in calculus, you'll be able to work with cosines of anything. The two doesn't really matter that much very easily. And so, and cosine squares and sine squares are not so easy to deal with. So what you can do is you can convert these cosine squares and sine squares into essentially cosines of 2x's. All right. Okay, so definitely you'll see this in probably towards the end of first semester calculus or the beginning of second semester calculus. And if you're in a quarter system, then you'll probably see it at the in second quarter calculus. All right, so that's the double angle identity for cosine. Naturally, we would want to know the sine version of that. So sine of 2x. And again, we just use the same idea. Sine of 2x is sine of x plus x. That's equal to, well, sine of the first guy, cosine of the second guy, and then plus cosine of the first guy times sine of the second guy. And of course, we end up with the same thing. So this is 2 times sine of x cosine of x. And this is actually, again, going to be very useful. This one is actually extremely useful in calculus as well, around the same time that the cosine one is useful. Okay, for you can figure out tangent of 2x. What would that be equal to? All right. The sine and cosine ones are far more important than the tangent one. All right. Let me do a kind of a convoluted example of using this sine identity, right? So sine, let's say we want to know what sine of 7 pi over 6 is, right? Like I said, there's often multiple ways to do these calculations just because we have so many identities available to us. So maybe a fun thing you can do is try to figure out a way to do this that's different from what I'm going to do right now, because what I'm going to do is slightly convoluted. So what is this? The way I'm going to do this is equal to sine of, because I know the double angle identity, I'm going to write this as sine of 2 times something. So what is 7 pi over 6? 2 times what? Well, it's 2 times 7 pi over 12, right? Because then the 2 and the 12 cancel to become 6. And the reason I'm doing this, it seems kind of ridiculous, but the reason I'm doing this is because I already know, actually from the last lecture that we just talked about, sorry about this jumping around. I already know sine of 7 pi over 12, right? We just talked about that in 3.4 from this week. And so this is going to be 2 times, and now just quoting from the identity, sine of x, cosine of x. So 2 times sine of 7 pi over 12 times cosine of 7 pi over 12, right? And this guy here, we just talked about this in 3.4. This one right here, we just talked about in 3.3, right? And so actually, I'm not even going to finish the problem. I'm just going to say, well, we know we can do this. This is something that we know. That's something that we know. And so therefore, we actually know how to do 7 pi over 6. All right. Okay, and so let me write this as easy in quotes, of course, because nothing is actually that easy, but easy in the sense that we already know how to do them, right? And that's always what we want to look for in math, right? You always want to break down something that you don't know or is complicated, like this one here, into, or the sign of this guy here, into something that's into something that you know how to work with, right? So this one right there and that one right there. Okay, so those are my double angle formulas. So now let's talk about the half angle formulas. Identities or formulas. So these guys are a little bit more complicated. What happens here is we're going to use the identity for cosine. So let me write that down again. the double angle for cosine. So cosine of 2x. Let me write it like, because what's going to happen is things might get look a little confusing. So I'm going to write it like this: cosine of 2 times anything. So let me put a box to represent anything. All right, is equal to cosine squared of the first thing. I'm sorry, of that thing, minus sine squared of that thing. All right, and what I'm going to do is I'm going to compute right now cosine of 2 times 1/2 x. All right, and this looks kind of silly, but the idea here is cosine of 2 times 1/2 x, that's equal to cosine of just x, right? But if I use the identity from above, from this one right here, then I'm going to be able to break down this cosine of 2 times 1/2 x into just cosines and sines of 1/2 x, right? So this is going to be cosine of, right? And this is 2 times 1/2 x. So I'm going to put the 1/2 x together as my box, right? Right there. And so this guy goes there, this guy goes there. Okay, and so we end up with cosine of, squared of 1/2 x minus sine squared of 1/2 x. Okay, so we're kind of discovering the formula, the half angle formula, in a very different way that we've discovered our previous formulas. So the previous formulas, for example, if I wanted cosine of alpha plus beta, I just wrote down cosine of alpha plus beta equals, and then I did some computation, right? When I wanted the sine of 2x, I just wrote down sine of 2x equals, and I did some computations. But this one is a little trickier in that I'm not starting with cosine of 1/2 x. I'm starting at cosine of x. And then I'm very kind of cleverly writing x as 2 times 1/2 x. And that what allows me to break down cosine x into terms that involve 1/2 x, cosine squared 1/2 x, and sine squared 1/2 x. Okay, now this looks kind of terrible because I have cosine and sine of 1/2 x's, but I always remember my fundamental identity, which tells me I can convert, for example, the sine squares into cosine squares. So this actually is cosine squared of 1/2 x. Oops, sorry, 1/2 x. Minus, and as sine squared is 1 minus cosine, right? Squared. So this is 1 minus cosine squared of 1/2 x, like that. Okay. So this guy right there converts directly to that guy right there. Okay. All right. And the reason I did this is because I have a cosine squared 1/2 x right there, and I have literally the same term right there. Okay. So when I simplify this, this simplifies to this minus sign distributes into the 1, and it distributes into this minus cos squared. So minus and minus becomes plus. So ultimately, what I end up with is 2 cosine squared 1/2 x, and then minus 1. All right. So ultimately, from the top to the bottom, what I've ended up with is cosine of x is equal to 2 cos squared 1/2 x minus 1. And so if I throw everything to the, if I isolate the cosine 1/2 x, right, I'm going to end up with cosine of x plus 1 is equal to 2 cos squared 1/2 x. And so cos squared 1/2 x is equal to cos x plus 1 all over 2. And so if I take the square root of both sides, cosine of 1/2 x is equal to plus or minus square root cosine of x plus 1 over 2. Remember, whenever you take the square root of both sides of an equation, you have to pop out a plus or minus. All right. Okay, and this is the identity that we're looking for, or this is one of the identities that we're looking for. It tells me how to calculate cosine of half of an angle when I know cosine of the full angle, right? On the left-hand side is cosine of half of x. On the right-hand side is cosine of x. All right. There is a little bit of ambiguity in that I have this plus or minus. but whenever I know the angle that I'm putting in, I can figure out that plus or minus, right? For example, if the angle I'm plugging in is between 0 and pi over 2, I know cosine should be positive, so I know I should choose the plus. Whereas if the angle I'm plugging in, half of the angle I'm plugging in is between 90 degrees and 180 degrees, I know cosine is negative there, and so I should choose the negative one. All right. Okay, so in terms of applications, right, this means that we know how to calculate cosine of pi over 12 in a different way that from what we did before, right? Before we wrote cosine pi over 12 as cosine of pi over 3 minus pi over 4, right? So before we did this. And then we used our cosine identity to get this. But now we can actually do it in a different way. Cosine pi over 12, we can think of pi over 12 as 1/2 of pi over 6, right? And the reason I do that is because I know that pi over 6 is a very comfortable angle for me, right? I know a lot of values for pi over 6. And so in particular, in this case, this is equal to, and now I'm just going to quote my formula, plus or minus square root cosine of pi over 6 plus 1 all over 2. Okay. And what is cosine pi over 6? Well, that's equal to root 3 over 2 plus 1 all over 2. And let's clean this up a little bit. So this is just to make it a single quotient, 2 root 3 plus 2 all over 2 like that. And this is equal to plus or minus square root 3 plus 2 over 4. Okay. Oh, let me clean that up even more. This is plus or minus 1/2 root 3 plus 2. Okay, now plus or minus, right? We don't like that. We want to know exactly what the answer is. But pi over 12 is between 0 and pi over 2. So cosine looks like this. I like to do these using the graph. So there's pi over 2. Pi over 12 is somewhere here, right? Very small. And so we know cosine is positive here. And so that means that we need to choose the plus sign. And so ultimately this is equal to 1/2 root 3 plus 2. All right. Okay, one thing you'll notice is the formula we got for cosine pi over 12, or the expression we got for cosine pi over 12, look different from this one, but secretly they're the same. You can actually verify that they're the same by doing basically like a verify problem by manipulating both sides in certain ways, and you'll see that the two expressions are actually the same, even though they look slightly different. Okay, maybe you're not excited because of this, because we already knew cosine pi over 12. So something that's very new is because I know cosine pi over 12, now I actually can do cosine pi over 24, right? Because cosine pi over 24 is cosine of 1/2 of pi over 12, right? And then I can just use the same identity. This is plus or minus square root, and then again, I'm just going to copy down my identity right there, square root of cosine x plus 1 all over 2. X is now pi over 12 plus 1 all over 2, right? And then I know I'm all set because I just calculated cosine pi over 12 being right there, all right? And then I know this one is also a plus as well because I know cosine of pi over 24 should be a positive number, okay? So you can actually use this to get some new values for cosine that perhaps we couldn't have calculated before. Okay, so you'll find a few problems on the online homework that where you need to use this identity, and just always be aware that it's plus or minus. Whether it should be plus or minus depends on what that quantity is right there. whether that guy, cosine of that angle, should be positive or negative, depending on where it is. And you can always tell that from the graph, right? Between 0 and pi over 2, cosine is positive. Between pi over 2 and 3 pi over 2, cosine is negative. And 3 pi over 2 to 2 pi, it's positive again. Right? You could do it also from the unit circle, but I think it's a really, really good idea to get, in a way, to work natively with the graph as much as possible, because the graph is just so important in terms of understanding cosines and sines and trig functions in general. All right, so that was cosine, the half angle identity for cosine. The question now is, what's the half angle identity for sine? And one thing you could do is maybe pause for 5 minutes and try to see if you can get it for sine, because it's perhaps not as obvious as you might think. Or maybe the technique is not as straightforward as you might think. And it's always good to try something first before it's explained to you, because then it helps you kind of understand and appreciate why it was done perhaps in a different way than what you might have thought. All right, in any case, let me do it now. What about, so the question is, what about sine of 1/2 x, right? So the way we're going to do this is actually, so this is why I said that it might not be as obvious. The way we're going to do it is we're actually going to start with cosine again, all right, as opposed to sine. We're not going to use the sine identity to get sine of 1/2 x, because what happens is we're going to start with cosine x, and again, literally the same step. Cosine, this is cosine 2 of 1/2 x, right? And again, this is cosine of a double angle, so 2 times that guy right there. So this is cosine squared of 1/2 x minus sine squared of 1/2 x. And last time, when we wanted the identity for cosine of 1/2 x, we converted the sine into cosine, right? But now, since we want the identity for sine, we're going to convert the cosine into a sine, right? Which we can do, right? Cosine squared is 1 minus sine squared. So that becomes 1 minus sine squared of 1/2 x, right? And then we still have this minus sine squared of 1/2 x. So ultimately, we get 1 minus 2 sine squared of 1/2 x. All right? And now this is what we want, because from the start, we have cos x, and then that's equal to, at the bottom, 1 minus 2 sine squared 1/2 x. And doing the exact same thing as what we did just now, solving for the sine squared, we're going to end up with cosine x minus 1 equals minus 2 sine squared 1/2 x. And so if I divide by 2 on both sides, I can write this as 1 minus cosine x all over 2 equals sine squared 1/2 x. And so if I square root both sides, equals square root 1 minus cosine x over 2, and then plus or minus. Okay. And the plus or minus, which one should it be? Again, it depends on this angle right there and how sine behaves with that size of an angle, right? So if that angle is between 0 and pi, it's going to be, I should choose the plus, because sine looks like this. And between 0 and, if 1/2 x is between 0 and pi, right, I'm living here. And if 1/2 x happens to be between pi and 2 pi, then I need to choose the negative sign. All right. Okay. So in terms of applications, literally the same ideas. Now I can do an alternate computation of sine of pi over 12 by thinking of it as sine of 1/2 of pi over 6, right? And you can do all sorts of computations. Again, if you've done that one, then you can do sine of pi over 24, right? And of course, if you've done that one, if you want to really make yourself suffer, you can do sine of pi over 48, because pi over 48 is half of pi over 24, and so on. Okay, so again, we end up with a lot of values of sine that we can compute now where previously we couldn't, we didn't know how to compute. All right, maybe this seems kind of ridiculous. So let me do one that maybe looks a little kind of not as nasty, right? Sine of pi over 8 is one that is relatively straightforward, right? It's not like pi over something like 48, right? But this one is something that before we couldn't calculate, but now we can. This is sine of 1/2 of pi over 4, right? And again, the entire point of breaking it down this way is that we know cosines and sines of pi over 4, right? Okay, so in degrees, this would be a sine of half of 45 degrees, so 22.5 degrees, right? So that's definitely a value of sine that we couldn't compute previously. Okay, actually, maybe I should, I guess I should give an explicit example where we end up having to choose the negative sign as opposed to a positive sign, just to kind of emphasize that it's definitely a possibility. So let me do it with the cosine. So for example, cosine of 3 pi over 5, right? What is that? That would be plus or minus. If I wanted to use the half angle identity, this would be cosine of sorry, I've been writing it like this, cosine of 6 pi over 5 plus 1 all over 2. Right? Because 3 pi over 5 is 1/2 of 6 pi over 5, right? So in this kind of made up problem, for example, maybe for some reason we've calculated cosine of 6 pi over 5, and so we know it. And now the question is, what is cosine of 3 pi over 5? All right. But the real issue here I want to emphasize is that this is a situation where I need to choose the minus sign, because 3 pi over 5 is bigger than pi over 2, right? So here's pi over 2. 3 pi over 5 lives somewhere here, right? Because 3/5 is bigger than a half. And so cosine should be negative in this region between pi over 2 and 3 pi over 2. And so in this particular example, we need to choose the minus sign. All right. Okay, and another comment I want to make is, let me write down my formulas again, just because I've scrolled them away so far. Cosine half x, so this is the half angle formula for cosine, square root. And our book, and I think a lot of books write it like this, cosine of x over 2. Maybe this way is actually better than the way I've presented it. Sorry, just because I've been writing cosine plus 1, and I'm writing now 1 plus cosine because maybe this is a little better, because now there's a bit of consistency between sine and cosine, right? With cosine, it's a 1 plus, and then with the sine, it's 1 minus. Maybe it helps you remember these identities. Okay, by the way, again, if you're bad at memorization, which I am, you don't even have to memorize these two identities. What you do is just remember that you can always reproduce them from the double angle identity of cosine, right, if you need it. And again, maybe that sounds like more work, but in a way it's not, because when you memorize something, it's really, really easy to memorize a plus into a minus, right? And then there's no hope, because there's no way that you'll know whether it should be a plus or minus, right? Because it's just pure memorization. But if you reproduce it from kind of scratch, or from the identity for cosine of 2x, the double angle identity for cosine, you kind of understand where it comes from a little better. And so there's more chance you'll get the identity correct in a way. Okay, but again, hopefully you'll do enough problems that it's kind of automatically committed to memory. Okay, in any case, these are my two identities that we just talked about. One thing to note is that whenever you see square roots, you should be slightly uncomfortable, because whenever you have a square root, there's a chance that that thing is illegal, right? Because if square root, the thing inside the square root is negative, then the whole expression is illegal, right? So that's one question you can ask here. is it possible that these two guys in here might be illegal, right? Maybe this guy here or this guy here. Could it turn out that this guy up here is negative, and then you would be ending up taking a negative square root of a negative, right? That would be bad, right? But it turns out that it never happens because we know, for example, for this one down here, cosine is never bigger than 1. And so 1 minus cosine is always going to be a positive number, right? So you'll always be taking the square root of a positive thing. Same thing up here. Cosine is never less than minus 1. And so 1 plus cosine is always going to be positive. And so this thing under the square root is always going to be positive. And so the square root is always going to be legal. All right, so there's no actual potential problems because of that square root or those square roots. All right, what about tangent? Well, I don't really care because the identity for tangent, you almost never use it. You almost never really see it. So in a way, who cares? But if you really did care, you could just use sine over cosine. Okay, if you really needed it. So you're going to end up with an expression that is not in terms of tangent, but that's fine. The main point here is that you're able to get a trig function of half of an angle in terms of the trig functions of the full angle, right? So again, if you know tangent of 68 degrees, then that means you'll know tangent of 34 degrees, okay? All right, so I'm definitely not going to dwell on this guy here. I'm not going to even bother to write down the formula. I don't think that really it's worth our time. Okay, one note. On the homework, there's a problem from the book for this week, the paper homework for this week. There's a problem from the book where that involves half angles. And I want you to do it using considering the formulas for cosine and sine. And I'm going to say that you're not allowed to use the formulas for tangent. All right, just so that it makes the problem a little bit more interesting in terms of how to work it out. And again, I think working the formulas for tangent is kind of a waste of time just because it's so rarely used. Okay, finally, I want to do at least one verify problem for this week, just so that we can see it again, see the technique again. But really, it's not going to be anything new in that the verify technique is still the same as before, except you just have more identities that you might need to take into consideration. Okay. By the way, the half angle identities, they're kind of cool. We use them to calculate a few angles, but in practice, we're not going to be using them very much in our class. And so in a way, after the end of this class, even if you are going to be taking more math, more calculus and stuff like that, it's actually okay to kind of forget the half angle formulas. But you really should remember that there is a half angle formula, and that if you need the half angle formula, you can either look it up or you can reproduce it from the double angle formulas. All right. So the actual formula itself, you don't have to memorize after the class is over. For this class, of course, you should know it. But after the class is over, it's something that it's okay to memorize, to forget. Just make sure you remember that such a formula is available for you, that it does exist. All right. The double angle formula is far more important. So those you should actually try to know, especially if you're going to be doing calculus. All right, but those we'll actually be looking at in the future in our class. Okay, so verify. Let's see. So let's verify the identity cosine of, let's say, 2x is equal to 1 minus tangent squared x over 1 plus tangent squared x. All right. Okay, and we're just going to do the same verify technique, except we'll use some of the new identities. So let me do my answer here. And again, I think it's very good to be very disciplined with these. Cosine of 2x, is this equal to, right, 1 minus tangent squared x over 1 plus tangent squared x? And again, the question mark means I'm not sure whether it's true yet. I'm trying to confirm its truth, right? Okay, so this is equivalent to, and again, what my goal is to simplify either side or both sides or interact the two sides, right? So that I can tell, so that I get an equality that's obviously true, right? I want to work towards an equality that's obviously true. So my thought process here is that I have tangent of just x here. I have tangent of just x here. There's no way I can kind of check whether they're the same if I have tangent x's on one side, or trig functions of just x's on one side, and then trig functions of two x's on the other side. So what I really want is everything to be in terms of trig functions of just x, right? So my first thought is to convert this cosine 2x into trig functions of just x. So that means double angle identity. And so I end up with cosine 2x is equal to cosine squared x minus sine squared x, right? That's my double angle identity. And so that's equal to question mark 1 minus tangent squared x over 1 plus tangent squared x. Okay. All right. Again, this maybe doesn't look as compact as the line above, but mathematically it's easier to work with because everything is trig function of x, trig function of x, trig function of x, trig function of x. So there's more chance that they'll interact nicely. All right. Okay. And as usual, there's a lot of ways we can go about doing these problems. Everybody, probably will do this problem slightly differently if we just did them independently. But as long as you kind of get to the, your last line is an equality that's obviously true, then it's okay. All right. So the way I'm going to choose to do this is I'm now going to work on the right-hand side. Oops. And my thought process is that I would like everything in terms of sines and cosines, because if I have tangents and sines and cosines, it's harder to tell whether two things match or not, right? Whereas if everything is a sine or cosine, it's much easier I have fewer things to worry about, right? I only have sines and cosines, not sines and cosines and tangents. So I'm going to convert both these tangents into sines and cosines. So 1 minus sine squared x over cosine squared x. And on the bottom, 1 plus sine squared x over cosine squared x. All right. Okay. And again, this step seems more complicated. This line here seems more complicated than the previous line, but it's in a way mathematically simpler because there's fewer variety of trig functions now, right? Just sines and cosines. Okay, now the right-hand side is really messy, but I noticed that there's cosine x's on the bottom for both of them, right? And so my thought process here is I'm going to multiply the top and the bottom. Let me actually do it up here. I'm going to multiply the top by cosine squared x and the bottom by cosine squared x. And my thought here is that if I do that, then this cosine squared x down here is going to cancel away. And this cosine squared x down here is also going to cancel away. And so I'll end up with, instead of a fraction on top of a fraction on top of a fraction, right? Quotients over quotients, which is horrible. I'm just going to end up with a single quotient. Okay. So if I do that, I'm going to end up with cosine squared x times 1. And then cosine squared x times sine squared over cos squared, but those two cancel. This coses cancel. So I end up with cos squared minus sine squared on the top. And on the bottom, again, I distribute the cos squared x in. I get cos squared x plus, and then the cos squared x's cancel, and sine squared x like that. Okay. All right. And again, for every step, I have some sort of thought process, right? So what you don't want to do is just randomly, in a way, try things. You want to always have some justification for why you're doing the step that you're doing. Otherwise, you could run into trouble because there's always an infinite number of things you could try, right? So if you're just randomly trying things, the chance that you'll get to something that, looks good is very small, right? So every step you do, you want to have some justification for why you think that doing that step is going to make things clear up, right? Or clean up a little bit. All right, so that's why I've kind of been careful about justifying every step and explaining why I'm doing every step. Okay, now this is actually really great because cosine squared plus sine squared is our fundamental identity. That's equal to just 1, right? And of course, we notice as well, this top up here is literally the same as the left-hand side. So we know we're all set, right? So I kind of, in a way, don't even really need to write the next step, but I guess I should for completeness. Minus sine squared x, is this equal to cosine squared x minus sine squared x, right? Just quoting the fundamental identity. And now, obviously, the two sides are literally the same thing. And so the answer to this question mark here is yes, right? They are indeed equal. And so this question mark here, yes. So that question mark here, yes. So that question mark here, yes. And finally, this guy is yes. This left-hand side is indeed equal to this right-hand side. And so therefore we verified that this identity right here is actually valid, that it's actually true. Okay. All right. So that should be it for this section. It's a whole bunch of identities. We've learned a lot of identities over the last few lectures, but ultimately, if you think of them all as coming from the cosine identity, it's perhaps not as overwhelming, right? So if I just quickly review what they were, right? Cosine of something plus something else, and let me switch to x plus y, just for some variety, right? Instead of using alpha and beta, cosine x, cosine y, minus sine x, sine y, right? We have the negative version of this. I'm going to write this smaller just because it's very minor in that it obviously comes from the one above it, all right? So cosine x, cosine y plus sine x, sine y, right? And then we have another major one. We talked about this in the last section. Sine first guy, cosine second guy, plus cosine first guy, sine of second guy. And then we have kind of the minor-ish one, which is the subtraction version of it, which again, you don't really need to memorize because you can easily reproduce it from the one above. Okay. And then we got the double angles. So cosine of 2x equals cosine squared x minus sine squared x, right? We have the sine one, sine of 2x is equal to 2 sine x cosine x. And again, this one is actually very, we might not be using it too much in our class, but this one in particular is very useful in calculus. Actually, the one above as well. Okay. And then we have the half angle formulas. So cosine of 1/2 x is equal to plus or minus square root 1 plus cosine of x, 1/2 x over 2. And then sine of 1/2 x equals plus or minus square root 1 minus cosine x over 2. And in terms of the relationships between them, this guy got you that. This guy got you that in kind of an easy way. This guy got you that, right? The original guy up here got you that in a very easy way because 2x is x plus x. This one got you the sine version right there. And then the cosine 2x, let's try a different color, I guess. Oops. The cosine 2x got you that one, and also got you that one, in combination with the fundamental identity, right? Where we convert cosine squared into 1 minus sine squared, or sine squared into 1 minus cosine squared, depending on which of the two half-angle identities you wanted. All right, so even though it looks like we have 1, 2, 3, 4, 5, 6, 7, 8 identities to memorize, in a way, there isn't really that many. And again, really importantly, we have completely explained why each of these are true, right? Except for this first one up here, which we will explain in the near future.